Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, bitwise and for numbers range. So basically we get two numbers, left and right. So basically they represent a range, closed range from left to right. So including left and including right. And what we want to do is return the bitwise AND operator of all of the numbers in this range. Okay. So for example, 5 to 7. We want to return 5 and 6 and 7, and the result is 4. Okay. For this one, we want to return the end from 1 to 2, 3, all the way to this big number. Okay. So that's what we are asking. And notice here the range can be really big, like in this case. It can be even up to the last number that is created with 1 bit, 32 1 bits. Okay. So now, knowing this, how can we solve it? Well, we definitely can't just do something like for x in left to right, and then just end x with maybe a result, something like a result here equal to left, maybe from left to 1 to right, and do res and x. We can't do this because this won't pass. Even like just in this example 3, it won't. So what can we do? Now, the first thing to think about is, okay, what is this AND operator? Well, AND operator, if you do 1 and 1, it's 1. That's the only case where you get 1. If you do 1 and 0, you get 0. 0 and 1, you get 0. 0 and 0, you get 0. So this is important. So how do we solve it? Well, with these binaries, it's good to just do some examples and see what it will look like. So I have here just basically a couple of examples. Let's first just start with the simplest 5 to 7, okay, and see if we can find some pattern. So what I'm doing here basically is just going from left to right, inclusive, and just printing the binary, but I'm padding it here so that we see all the 32 bits representation, okay, from 31 to 0. So that's what we see here, okay. So the first thing you notice is that for all the numbers in between these two, right, you will never have a 1 here, right, because both right and left stop, the ones stop here. So it doesn't make sense to have a number in between with a 1 here, because if you have a number in between with a 1 here, that number will be bigger than the right number. So that's the first observation, is basically we can only have 1s. Because also in AND, remember what I said here, in AND, all that matters to get a 1 is that both are 1s. Okay? So you can't have a 1 here if you don't have a 1 here. At least here in the bigger one. Okay? Because if you have it in this one, you would at least have it either here or have a 1 here. Okay? So that's the first observation. What other observations can we make? Now look at the number here in between these two, okay? It has a 0 here. So what this tells us, if we end this, then 1 and 0, it will become 0. And now if you end with any other 0, you will get 0. If you end these, you get 0 here, so you get 0 here. And then if you end here, you get 1, okay? So notice what happened here. What happened is that in the first position, where the bits are different in the left and right, from there on to the rest, we have zeros. Right? So the first idea here to think about, but we will need to try more examples to see if it's valid, but the first idea here is that the prefix, we need to find the common prefix from the right. And basically stop when we find so stop when we reach the first bits different between left and right. From the right, basically come prefix of left and right, from right direction, basically. So basically, using the most the rightmost bit, rightmost to leftmost bit. Okay, but let's try a couple of other examples. Let me try maybe just so you can see. Let's try maybe just up to 10 and see what happens. Okay, up to 10, and let's print and see what happens. Okay, so let's run this. Okay, so look, let's see. So you can see here the right bit has a 1 here, okay, in a position bigger than the left one. But you can see we will have a 0 here because the smaller numbers, one of them would have the same binary as the left one. Even if you don't have it, already this cancels out. The end already cancels out this bit. Okay, so that tells you first that this bit is going to be 0. Okay, but if we look at the other numbers, because they are in between, there will be one with zeros, which will cancel all the ones here. So basically, again, our condition here applies. Just do the common prefix in the first bits that are different between left and right, stop and return that. And that would work here because all of these bits will cancel out with each other, and all the one remaining is the first one that we find in left or right, which is this one, but that one will cancel out as well because the bits are different, so we can return. So it's valid as well here. Now again, let's pick a bigger example, 2 other big examples, and just see if this pattern still holds. Okay, sorry, I need another print here, and let's do this. Okay, cool. So we already seen this one. Let's look at this one here. Okay, so again, the first bit, different bit, is this one between the 2. So our hypothesis is that we can return here with 0. But let's see if that applies. If you look at these and you end them together, all you need to look at is this 4 zeros, because this already cancels out all the ones here. And this works because if you have a number with 1 here, then and 1 with 0, then you would have a smaller number that has all the zeros in between, right? This is one way to think about this. This is like this is just like in decimal. If you have 1 7 1 maybe 2 8 5 6 8 as your left number, and maybe as your right number you have 2 8 2 8 9 9, then all the numbers in between will have, you would have 2800, right? Okay, so, and all the numbers in between will have a prefix of 28. Okay, and so just similarly here with the binary, if you have either these ones are the same, and that way we'll get a 1, all that matters is the first, and we'll get a 1, and we can proceed to the next because we know the other ones will have a 1, or they are different, then we know we'll have 1 with zeros. Okay, now the other thing is that what if we have a 1 here? So if we have a 1 here, then this would be 1. Now if we have a 1 here in both, then everything in between will have a 1. But if we have a 0, we'll have something like this that cancels out. So basically what this tells us is we can just look for the prefix of the left and right numbers, and as soon as we find the first bits that are different, we can return. But if we don't find it, we can just put 1 in that position and proceed to the right, to the left, right? So that's the core idea here. You can look more at more examples, but you will see that this applies. So here we have a 0. We got this one that will cancel all the ones because we'll end all these numbers together, right? So that's the core idea here. I hope this is clear. Let's go and implement the solution. So we said we want to find the longest common prefix and stop at the first different bit. So let's have our prefix, and that's what we'll return. And then let's call it, let's go for, we want to look for 31 bits. So we want to look from the range of 31 to 0. So that would be 32. And each time we go down. So this is so that we go from right to left, just like we did here. And what we will do is we check if the left bit is set. Left basically means the bit in the left, in this left number. And we want to check if the bit in right is set as well. So basically the bit at position I in left, whether it's set, and at position I of right, whether it's set. So how do we do that? Well, in binary you can check just by ending with 1. With basically, let's say I is equal to 3. Then you will just end with the I at position 3, right? Okay? Sorry, 1 at position 3. Okay? So we'll basically set the bit at position I and end it. And if there was a bit set, then we'll have 1 and 1. So we'll have a 1, which means this bit is set. But if it's not there, if it's 0, then 0 and 1 will give us a 0. So we will get that it's not set. So it's set when this here gives us a 1. And so when it's different than 0, basically. Because again, this gives us a number. So if it's 0, then the entire number would be 0. But if it's a 1, depends on the position, but it would be a number different than 0. So that's what we are looking for here. And we can do the same thing for right, except this would be right here. And now we check if the bit is the same, then we are good. But if the bits are different, we should stop. We should break as soon as the bits are different. Because what this means is we will get something like this with all zeros after it, which will cancel all the ones. And so otherwise, if not, then what should we do? Well, we set it if the left bit is set. So if one of the bits is set, okay, which means both are 1, then we can set that bit 1. But if it's not set, that means we have a 0 and we have 2 zeros and we should set it to 0. But setting it to 0, we can just not do anything because there is already 0. Okay, so if left bit is set, I don't need to check if right bit is set, because if left bit is set, that means right bit is set, because we already determined that they are either both set or both not set, right? And so prefix, we OR it with position I. So what this basically will do is it will set the bit at position I in prefix. Okay, and I hope that was clear. Let's run it. Let's submit, and that passes. Okay. Now in terms of time complexity, this is constant time because it's just we do 32 iterations, right? Now the core idea of this problem is to try it out and see examples. It also helps if you sort of try to map it to decimals. Yeah, so that's pretty much it for this problem. Thanks for watching and see you on the next one. Bye.